Hello students, your COMEDK 2024 exam is there. So in this video, we'll be doing a complete revision of the total physical chemistry. So I'll be discussing all the important topics, important subtopics, important formulas and the type of questions that will be asked from this. So from this particular video, you can easily expect 18 to 20 MCQs or more than that because the syllabus in physical chemistry is reduced. So number of questions might increase. So around 20 to 25 also you can say MCQs you can expect. So please watch this video completely, note down all the important formulas, all the important concepts and then revise them and before going to the exam. Okay, so let us start with this video. Please watch it completely. So first one is we'll see what all chapters are there. So the chapter is solutions, the most important topic. Then we have electrochemistry, chemical kinetics, thermodynamics, equilibrium, some basic concepts of chemistry and structure of atom. So we will not be discussing the complete chapter. We'll be discussing the key areas, the key concepts that you must revise at this last one day, right? Okay. So let us start here. First is chapter 1, solutions. So what are the topics in solutions chapter? Solutions and its types, concentration terms, Henry's law, Raoult's law, ideal and non-ideal solutions, colligative properties and Van 't Hoff factors. Okay, quickly we will see them. So first is your type solution and its types. The first category is based on the solvent. So if solvent is solid, then it is called solid solutions. Solvent is liquid, we call it liquid solution. Solvent is gas, we call it gaseous solution. And then based on composition, we have homogeneous and heterogeneous solutions. So what you have to do, you have to learn examples for each of them. Okay. Now coming to the most important topic, that is your molarity. Concentration term, number of moles of the solute by volume of the solution in ml into 1000. How to calculate number of moles? Given mass of the solute by molar mass of the solute. Okay, please quickly have to write down all the formulas with me. Okay, now coming to molality. Molality is number of moles of solute by mass of the solvent into 1000, right? Next is mole fraction. So mole fraction is number of moles of the particular component divided by the total number of moles. Okay. Now here, suppose there are two components, you know one more relation, XA plus XB is equal to 1. Okay, so now we have written 4 formulas. Okay, now, so just keep a count of the formulas, how many, like when you revise, we have 1, 2, 3 and then 4th formula. Henry's law. So what does statement? You need not remember at this point of time, just you have to know that the amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of the gas, of that gas above the liquid. The expression is very important. P of the gas is equal to kH into mole fraction of the gas. Formula number 5. Okay. Next, what is there here? P is the partial pressure, kH is the Henry's constant, X of the gas is the mole fraction. Now, one more thing that you have to remember is solubility. Okay. Solubility is inversely proportional to kH value. More is the kH value, less will be the solubility. Okay. Now, coming to the next one. We have Raoult's law. Okay, so Raoult's law statement also here, that is not very important, just you have to know that the vapor pressure of each component of the solution is directly proportional to its mole fraction. Just write down this much, vapor pressure proportional to mole fraction, 2 words. Okay, now what you can see, or you can just write in the terms of formula, P1 is equal to proportional to X1. Now formula for calculating the total pressure, right? So this is your formula number, we have 6, right? We wrote 6. So this is formula number 7, right? P total is equal to PAXA plus P2X2. So where P1 is the partial pressure of first component, P total is equal to P0AXA plus P0BXB. What is P0A? What is P0B? P0A is the pressure of pure component, P0B is the pure pressure of component B. Okay, so these two values XA and XB are their mole fraction, right? Now here one more formula we will add, that is vapor, the mole fraction in the vapor phase, right? YA and YB. So YA you write down PA by P total and YB is equal to PB by P total, right? So complete 8 formulas from solutions now till now written. Now let us go to the next one. Ideal and non-ideal solutions. This is very important, students. Questions are asked from here. Graphs are given about the interactions they are asking. Okay, so you have to remember they obey Raoult's law, does not obey Raoult's law. Delta H mix is equal to 0, not equal to 0. V mix equal to 0, not equal to 0. This point is very important. AB interactions is equal to AA and BB interactions. Here AB interactions is not equal to AA and BB interactions. Quickly you have to note them, like remember this one. Next we'll go to, in non-ideal solutions, what happens? There is two type of deviation, positive deviation and negative deviation. These points are also very, very important. So first, in positive deviation, AB interactions are weaker than AA BB interaction. Here AB interactions are stronger than AA BB interaction, right? Now if you see the total pressure is equal, greater than P1 x1 plus P2 x2, here the total pressure is less. Now positive deviation, delta H mix is greater than 0, delta H mix is less than 0. V mix is greater than 0, V mix is less than 0. Okay. Now you can just see the graph for here. In positive deviation, graph will be towards the towards top, and then negative deviation graph will be depressed. Okay. Okay. Now coming to azeotropic mixture. So what is azeotropic mixture? Just definition you should know, that they have the same composition in the liquid and vapor phase. Only have to write this much statement: same composition in liquid and vapor phase. Now they boil at a constant temperature. Okay. Now this is also of two types: maximum boiling azeotrope and minimum boiling azeotrope. So maximum boiling azeotrope, what is there? They show positive deviation. So those who are having positive deviation, they will have maximum boiling azeotrope. Okay. And one second, the solutions, okay, sorry, this is wrong. When there is negative deviation, okay, if there is negative deviation, then there will be maximum boiling azeotrope. You can see the examples here. And then for minimum boiling azeotrope, there will be positive deviation. Okay. So please change this one. Okay. Minimum boiling azeotrope will have positive deviation. Now examples you have to remember. Examples are very important. Now coming to the next one, colligative properties. So if you see, first one is, what is colligative properties? The properties of the solvent which depends on the amount of solute added. Okay. So now what is our first colligative property? That is relative lowering of vapor pressure. What is the formula for here? Only formula will remember. What is the concept? When a non-volatile solute is added, the vapor pressure decreases. So we have the formula delta P by P is equal to P naught minus P by P naught is equal to XB. Okay. Right. So we can write the formula once again here. Delta P by P, that is P naught by P naught is equal to XB. Okay. I think this is 9th formula. Okay. Formula number 9. So here what is P naught? Pressure of the pure solvent. What is P? Pressure of the solution, that is after adding solute, what pressure has become. And XB is the mole fraction. Right. You can easily calculate this one. Next we'll go to the next formula, that is formula number 10. Elevation in boiling point, delta TB is equal to KB into M. So here questions are asked. Delta TB is equal to KB into W2. Molality formula we can write into 1000 by W1. Right. So in this what happens? M2 questions, most of the time you will find M2 is asked in the question. Okay. That formula we can use. Then next one, if we see depression in freezing point. So this is your formula number 11. Same formula, delta TF is equal to KF into M. Now coming to your osmotic pressure, that is pi is equal to CRT, where C is the molarity, R is the gas constant, 0.0821 liter ATM mole inverse Kelvin inverse. Okay, and then T is the temperature. Now this is very important term. Two solutions having the same osmotic pressure are called as isotonic solution. So you have to remember what is an isotonic solution. Okay. Now coming to next question, next topic, that is your Van 't Hoff factor. So this Van 't Hoff factor can be like association and dissociation. From here many questions are asked, like they will be giving you solutions, like 4 options are given, which is having the maximum boiling point, which is having the minimum boiling point, or which is having highest osmotic pressure, relative lowering of vapor pressure. So you should be able to calculate the value of I, right? So I means number of ions dissociating. Okay. So for example, Na3PO4 is there. What will be the I value here? 3 ions from here, 1, so I value will be 4. So whose I value will be more? There the freezing point will be, boiling point will be maximum, right? So we can do in this way. Now there is also to calculate the degree of association and degree of dissociation. So one second, we'll see here 12th formula. This is 13th and this is 14th. So degree of association is alpha is equal to I minus 1 by n minus 1, and for degree of association alpha is equal to I minus 1 by n minus 1. Okay. So now we are done with the physical solutions chapter. So how many formulas we saw in solutions chapter? We got total 14 formulas. Okay, very easy formulas. So just revise them. Do some numericals from this. So you can do our top 30 questions from the solutions chapter. Do them once and then you will be completely ready for this chapter. Any question come, you can easily attempt. Calculator is also there, so there's no problem of like getting wrong answers in calculation. The only thing you need to know is the concepts and the correct formulas, right? Okay, so now let us go to the next important chapter, that is electrochemistry. So this chapter is little difficult, people think, but your questions are asked very easy and from some specific topics only. You did not have to do all the things, right? So let us first quickly see. Type of cells are there, conductance is there, and commercial batteries are there. Okay, now if you see, in type of cell we have two types of cell. One is your galvanic cell and another is your electrochemical cell. Galvanic cell, what does it do? Chemical energy to electrical energy, and it is a spontaneous process. Electrochemical cell just converts electrical energy to chemical energy, and it is a non-spontaneous process. Okay, nothing to like questions will not be asked from here. We'll go to galvanic cells. What are the topics under galvanic cell? We have working of a Daniell cell, cell notation, electrode potential, cell potential, Nernst equation, equilibrium constant, and relation between delta E and delta G. So here questions are asked from Nernst equation, equilibrium constant, delta and delta G, and then we have cell notation, electrode potential measurement. Okay, these are the important topics here. So first of all, working, I think everybody will be knowing, so we can just discuss quickly here. So what is happening? If you see, zinc will be there, it will lose electrons and come to the surface as come to the solution as Zn2 plus. The electrons move through here and the copper 2 plus in the solutions get reduced. So here we have to remember one very important abbreviation, LOAD. Okay, what is that? Left oxidation, anode, negative. Okay, so that's it. That what does that mean? On the left hand side, there is the anode is present, it is negatively charged, and on anode there is always oxidation, on cathode there is always reduction. Okay, now how to represent a cell? First, suppose you have to write the anode side. Okay, that is the oxidation, then one salt bridge, and then you have to write the cathode, that is reduction. Okay, so that is how you have to write the cell notation. Next, coming to electrode potential. So we need not study this much here, but you have to know that an electrode can be positively charged or a negatively charged electrode. Okay, now what is the electrode potential? The potential difference that develops between the electrode and the electrolyte is called as electrode potential. Okay, so each so on oxidation and reduction we have, here we have an electrode and an electrolyte, here we have an electrode and an electrolyte. So the potential difference between this electrode and the electrolyte will be called as oxidation potential. Here it will be called as your reduction potential. Now if you see here, what is the use of standard hydrogen electrode is used to measure electrode potential. Okay, so this one, like whichever electrode potential you want to measure, you have to keep that on one side, and another side you have to take hydrogen electrode, and hydrogen electrode potential is assumed to be 0. Okay, now coming to cell potential, how to calculate the EMF of a cell. This is very important, formula number 1 for electrochemistry. So solutions you have to remember, 14 formulas we have done, right? Now E of the cell at standard conditions is nothing but E naught of cathode minus E naught of anode. Here you have to remember that E naught value should be in the reduction form. Okay, it should be in the reduction form. Means what? For example, copper and zinc is there, right? We got this one, Zn2 plus, okay, and then copper 2 plus 2 copper. So it will be given the E naught value of Zn2 plus 2Zn. Okay, this is the reduction formula. You can see 2 plus 2, 2. Reduction is happening. So the reduction potential of zinc should be given, reduction potential of copper should be given. Then we have to take E naught of cathode minus E naught of anode. Means E naught of copper minus E naught of zinc. So that is why you have to remember, this is left side is always anode and right side is always cathode. Okay, cathode minus anode. Don't do mistake in this formula. It is always cathode minus anode. Okay, now we will go to the next one. Okay, now what is this Nernst equation? We have already calculated cell EMF, right? Then what is the use of Nernst equation? So cell EMF is calculated using this formula under standard conditions. Standard conditions means the electrolyte concentration is taken as 1 molar. Now if we change the concentration of electrolyte more than like any other value, then we have to use Nernst equation. Clear? Okay, now let us see what is there in the Nernst equation. E of the cell is equal to E naught of the cell. How we will calculate E naught of the cell? Cathode minus anode minus 2 point. So this value, okay, this value will become 0.059. You remember 0.059 by N log of product concentration by reactant concentration. Okay. So if this is the cell reaction, then you have to take product concentration divided by reactant concentration raised to the power of stoichiometric coefficients. So this is the where you people make, definitely many of the students make mistakes here. They do not consider the coefficients. Okay. So coefficients are very, very important. That has to be taken. Do not forget it while using the Nernst equation. Okay. Now what happens here? So we will calculate E naught E of the cell. So you can see under standard conditions, E naught of the cell will be higher, right? After that, under non-standard conditions, we get E of the cell. Okay. Yeah. Now coming to this one. For example, this reaction, will do one small example. Okay. Zn2 plus to Cu2 plus. Now if you see the cell reaction at oxidation, it will become Zn2 plus 2 electron, right? And here at cathode, it will be copper 2 plus 2 electron gives copper. So now if I add both the reaction, 2 electron will get cancelled. So I'll get Zn plus Cu2 plus will give me Zn2 plus Cu, right? So what will be the E of the cell? E of the cell will be E naught of the cell, that is E naught of copper minus E naught of zinc minus 0.059. How many electrons are involved? 2. So 0.059 by 2 log of product concentration by reactant concentration, only ions you have to take. So Zn2 plus concentration by copper 2 plus concentration. This is not 2 power, okay? It is like this written. Zn2 plus by copper 2 plus. Okay. Now let us do this one. Let us this one. We have this one. The Ni plus, so I'll write this reaction again. Ni plus Ag plus gives Ni2 plus Ag. Okay. So now if you see what is the oxidation reaction, Ni is getting converted to Ni2 plus 2 electron. Okay. Silver is getting converted from Ag plus 1 electron to Ag, right? This is undergoing oxidation. So this is anode reaction. Okay. And this is going reduction. So it is cathode reduction. Okay. Now if you see here, there are 2 electrons, here it is 1 electron. So this electron will be this equation you have to multiply it with 2. Then what I will get here, 2 Ag plus 2 electrons gives 2 Ag. Now you have to add both the reaction, anode and cathode reaction. So if I add both the reaction, what I'll get? So Ni is there. So I'll write here Ni, okay, plus 2 Ag. Okay. So we will get Ni plus 2 Ag plus, then Ni2 plus 2 Ag. Okay. Now if you see, now I want to write the E naught of the cell. So first we will calculate E naught of the cell will be equal to E naught of cathode minus anode. How to identify which is cathode, which is anode? I told you oxidation will always be anode, reduction will always be cathode. So that will be, it will be E naught of Ni2 plus, okay, sorry, E naught of Ag plus 2 Ag, because our cathode is silver, right? So E naught of Ag plus 2 Ag minus E naught of Ni2 plus 2 Ni, right? So this is the E naught of the cell. Now E of the cell will be equal to E naught of the cell, okay, minus 0.059, number of electrons is 2, log of product by reactant concentration. So you see in the product side only nickel ion is present. So Ni2 plus concentration whole divided by Ag plus concentration. Here I am telling this 2 people generally forget. Okay, this 2 stoichiometric coefficient you have to remember, right? So like this you can solve any Nernst equation question. Calculator is there. Again I am telling, it's very easy to score physical chemistry problems if you only know the formulas correctly. Okay. Now coming to the next one, that is equilibrium constant and Nernst equation. So at equilibrium what happens? E of the cell becomes 0, right? Then E naught of the cell will be equal to 2.303 by RT into log Kc. So questions will be asked you to calculate for log Kc value, or Kc value is generally asked. Then if we see what is the relation between delta G and E naught of the cell. So delta G is equal to minus NF E naught of the cell. These 2 reactions are also important. So I think we have first formula, this is Nernst equation is second formula, then we have third formula and fourth formula. Okay, till now we have written fourth formulas for electrochemistry. Now coming to electrolytic cell, so here we are studying about Faraday's law and products of electrolysis. Okay, so if you see first law, according to the Faraday's first law, the mass deposited, you can just write down this much, that the amount of chemical reaction is directly proportional to the amount of electricity passed. Okay, so what is the formula? M is equal to ZIT. So if it is not visible, I'll write here M is equal to Z into I into T. Formula number 5. Now what is Z here? Z is called as electrochemical equivalent. How to calculate it? Molar mass, okay, molar mass divided by N into 96500. What is this N? Number of electrons involved. Okay, now coming to second law. So if the two cells are connected in series, then when you are passing the same amount of current, then the mass deposited at cathode 1 by mass deposited at cathode 2 will be equal to equivalent weight of 1 by equivalent weight of 2. Okay, I'll see this formula. See, M1 by M2 is equal to E1 by E2. Now how to calculate E1? So M1 by M2 is equal to E1 by E2. E1 is nothing but molar mass of 1 by N1 into molar mass of 2 by N2. Okay, so this formula you have to calculate, and the question will be generally in this form, like they will give you one mass deposited and another mass you have to calculate. N1 and N2 are again the number of electrons lost or gained in the reaction. Okay, so that is done. So we are gone with sixth formula. This is very, very important, products of electrolysis, especially which one you have to remember, I'll tell. For molten NaCl, sodium at cathode and Cl2. Equations no need to remember, only the products. At cathode, sodium metal, at anode, chlorine gas. Now aqueous NaCl, if you take, hydrogen has more reduction potential, so hydrogen gas is produced and chlorine gas is produced. Now coming to dilute H2SO4, this one is generally like not asked, so but you can see at cathode hydrogen gas, at anode oxygen gas, and for concentrated H2SO4 at cathode hydrogen gas, at anode it is S2O8 2 minus. Now coming to next one is factors affecting electrolytic conductance. Okay, so we are now in the, so we have completed what? We completed the first types of cell we completed, galvanic cell and electrolytic cell. So in both, in galvanic cell we got some formulas, in electrolytic we got some formulas. So total we are done with now 6 formulas within the cells. Now we will go to the next topic, that is conductance. Okay, so ionic electrolytic conductance depends on what factors. Okay, electrolytic conductance means the conductivity due to the electrolyte. In electrochemistry, our conductor is electrolyte, so its conductivity depends on what factors. You can just remember, like question can be like, which of the following are the factors, which are not the factors, or like that some questions you may get. So first it depends on the nature of the electrolyte, whether it is a strong electrolyte or it is a weak electrolyte. Then the size of the ions produced and their solvation. Next, the nature of the solvent and its viscosity, concentration of the electrolyte, temperature. Okay, so these are the factors, you can just quickly point it down. Now let us see the next topic, that is conductance of electrolytic solutions. Okay, so conductance of electrolytic solution, here two important things that you have to know is kappa and lambda m. What is kappa? Kappa is specific conductance. Okay, specific conductance, and this one lambda m is molar conductance. Okay, now if you see here, what is the effect of concentration in both the conductance? Okay, so this one conductivity decreases, okay, with decrease in concentration. If you decrease the concentration, kappa value will decrease, but molar conductivity increases with decrease in concentration. First point is this one. Okay, so you can see kappa decreases with the decrease in concentration, but lambda m increases with the decrease in concentration. Now in the lambda m molar conductivity, we have two types of molar conductivity, that is due to strong electrolyte and this is due to weak electrolyte. In both the cases it will increase, but what is the condition why it increases in strong electrolyte? It is because of the increase in the mobility of the ions. And in weak electrolyte, why it increases? It is due to the increase in the dissociation of ions, right? Now, what is limiting molar conductivity? So, when you keep on diluting, the concentration becomes 0 and like almost equal to 0. That time, whatever is the conductivity, that is called as limiting molar conductivity. Okay. Okay. Now this is very important, Kohlrausch's law and its application. So what does Kohlrausch's law states? That the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation. So no need to like remember the definition and all, simply you have to remember, suppose we have an electrolyte AXBY, okay, then the molar conductivity will be equal to X times of molar conductivity of A plus Y times of molar conductivity of B, right? So that is what is your Kohlrausch's law. Now next we have to know is, what is the application of knowing this Kohlrausch's law? Where does it help? It helps us to calculate the molar conductivity of the weak electrolyte. Kohlrausch's law, students, very, very important. Okay, questions are asked repeatedly from Kohlrausch's law. In alpha value, you can find out lambda m by lambda naught m, that is molar conductivity by limiting molar conductivity. And then we can also calculate dissociation constant using C alpha square by 1 minus alpha. Okay. So what is it? It is interrelated, right? Once we get alpha value, we can get Ka value. And for getting Ka value, you need limiting molar conductivity value. And to calculate that, we need Kohlrausch's law. Okay. Get it? Now, okay, some products of electrolytes. Sorry, this is your commercial cells. Okay, 1 second. Okay, yeah. So these are your commercial cells. So we'll see some commercial batteries, their reactions. Okay. And it's not like all the batteries you have to remember. Certain cells, certain batteries I'll tell you which you have to, the reaction you must have to remember is the first one is dry cell. Okay, just you should know that zinc is the anode here and MnO2 is the cathode here. Next we have mercury cell. So mercury cell also you should know zinc and mercury are the anode and cathode respectively. Then if you see lead storage, in lead storage is very, very important. Learn its anodic reaction and cathodic reaction completely. This is your discharging reaction. The opposite will be the recharging reaction. Then nickel cadmium, you can just remember cadmium is anode and nickel is your cathode. Fuel cell reactions also you have to remember. Okay. So what you have to remember, reactions. Reactions is lead storage and fuel cell reactions, and others just you know which is anode, which is cathode. That is enough. Okay. Now here some important formulas we will discuss. Some more formulas here we will discuss. That is, so first of all, from Kohlrausch's law we got this one. 1 second. So we have written this formula, 6th formula we got. Now let us see, next formula is your 7th one, okay, 8th and 9th. Now coming to one more formula is there, that is kappa formula. Kappa formula, that is 10th formula, is 1 by R, okay, into L by A. Okay. So now how you are getting this one? So just if you know, we have formula is equal to R is equal to rho into L by A, right? Now 1 by rho is nothing but your kappa. So that is equal to 1 by R into L by A. Okay. So this is the formula for kappa value. What are its units? Its units are your S centimeter inverse, okay, or S meter inverse. This is the first formula. And next one you have to know is lambda m formula, that is equal to kappa into 1000 by C. Kappa into 1000 by C, where C is your concentration, kappa is again your conductivity, and 1000. So its unit is S centimeter square mole inverse. Okay, S centimeter square mole inverse. Okay, so total 11 formulas we got here. Okay, now coming to the next, third important topic, that is chemical kinetics. So again I'm telling you, we are not discussing each and everything from the chapter, only the important topics from where the questions are repeatedly asked. Those concepts we are revising in a detailed manner. Okay, so till now if you see, we have completed solutions chapter. We discussed 14 formulas. In electrochemistry we discussed how many formulas? We discussed around your 11 formulas, right? So apart from this, you have to learn the theory parts which I have told you to remember. Now going to chemical kinetics. Okay, so first of all, what are the important topics here? Rate of a chemical reaction, factors affecting rate, effect of concentration, integrated rate equation, effect of temperature, and then effect of catalyst, and then collision theory. Briefly we'll tell what is the most important. I'll take effect of temperature, integrated rate law, and effect of concentration. These three topics are very, very important. Okay, so now coming to first, rate of a reaction. Rate of reaction is of two types, you know, average rate and instantaneous rate. Average rate is when you calculate for a longer duration of time. Instantaneous rate is when you calculate for a particular instant. Okay, nothing too much to think. Then this is the graph for average and instantaneous rate. This graph questions are also not asked. This is important. Factors affecting the rate of the reaction: concentration, temperature, and catalyst. Concentration is there in detail, temperature is there in detail, catalyst is also explained in detail. Now first, if you see effect of concentration, so first of all you should know how to write. From here I'll tell you one more thing. Let us discuss here. Suppose you have a rate reaction A to the like this one reaction is there. Okay, will not put equal to, one second. So again, suppose you have a reaction 2A plus 3B gives 4C. Then how to write the differential rate equation, that you should know. So this is minus dA by dt. Okay, coefficient is 2, so we'll put 1 by 2 is equal to minus 1 by 3 dB by dt is equal to plus 1 by 4 dC by dt. Okay, so this is equal to what? Rate. This is how you have to write the differential equation. From here questions are asked, numericals are asked, like they will give you the rate and they will ask you dB by dt. They will give you like A concentration and they will ask you B concentration. So you have to first write the equation, then whose two values are asked or related, those relation you have to take and then solve it. Okay, so this is our first formula, differential rate law. Now we will go to our rate law, that is any rate law means the dependency. Okay, the dependency of a rate of a reaction on concentration is given by rate law. So rate law is equal to rate is equal to K into A to the power of N, where N is the order of the reaction, K is the rate constant. Okay, now we will see about order. What is order? So what does exactly order tell? See, we know that if concentration will increase, rate will definitely will increase, right? But whether how many times the rate will increase. Suppose you are making the concentration double, then will the rate also will become double, or the rate will become 4 times, or the rate will become half time. So that depends, that is given, that information is given to us by order of the reaction. Okay, now what is the definition? It is the sum of the powers of all the concentration terms in the rate law. Okay, so now if we see, so there is something called as molecularity also. Let us see the difference. So order is the sum of the powers of the concentration terms, whereas molecularity is the total number of species reacting in an elementary step. Molecularity you can tell by seeing a reaction, but order you cannot tell by just seeing the reaction. This is experimentally determined. Okay, it depends on the mechanism. Now this can be 0, negative or positive. It is always positive. It can be a fraction or a whole number. It has to be a whole number. Okay. Next thing, this is very important, questions are asked from here. What is the general formula to calculate the unit of rate constant? Rate constant, so this is my third formula. Our second formula is this one, right, where I wrote this one. Okay, now coming to this one here, third formula. Here how questions will ask, they will give you a unit or a K constant value and you have to predict the order of the reaction. For example, it is given for a certain reaction, K value is 1.6 into 10 to the power of minus 5 mole square liter minus square second inverse. Something like this is given. Now what you have to do is, you have to equate the power of mole with the power of mole here. So n minus 1 is equal to 2. So n will be equal to 3. So this is a third order reaction, right? So that is how you can solve it. Such questions are asked. Now coming to integrated rate laws, very, very important one. So for zeroth order, what is the reaction? A naught minus A is equal to KT. Okay, A naught is the initial concentration, A is the final concentration, K is the rate constant, T is the time. Now this is my fourth formula, right? Now for first order reaction, the 2.30 KT is equal to 2.303 log A naught by A. All of you must be knowing this formula, very important formula. This is my fifth formula. Okay. So next is your graph for zeroth order and first order. You can say if you have the concentration versus time graph, right? So we have this formula, A naught minus A is equal to KT, right? So I have concentration at any point of time, is that is A, versus time graph. So we will get this equation. I will write like this. This one I'll take this side and I'll write KT plus A naught, right? So you can see I can write it in the form of y is equal to mx plus c. So slope is negative with A naught as an intercept. Similarly, you can draw for first order reaction. Okay. Now graph is not that important, but you should know some basics how to derive the graph. If question is asked, you can solve it. Now this table is very, very important. You have to remember for the zeroth order reaction, differential rate law is minus dr by dt minus k. This is not here, half-life formula is there, r naught by 2k, and here 0.693 by k for first order. And then you have the integrated rate law, and you have the integrated rate law here, and the units of k is also given, right? So these are very, very important thing. Now coming to next one, that is effect of temperature. Very simple and easy concept. K is equal to A into e to the power of minus EA by RT. That is your Arrhenius equation. Here you have to remember, if activation energy will decrease, rate constant will increase. Okay, this point you have to remember. Next is what is here, what are the values? A is Arrhenius factor, R is rate constant, then K is rate constant, EA is activation energy, R is gas constant, and T is temperature. Now, if we have two different temperatures, when we increase the temperature, the rate constant increases, right? So when we have two different temperatures, T1 and T2, so at T1 the rate constant is K1, at T2 the rate constant is K2, then what is the activation energy, how to calculate? So that is the formula here, log K2 by K1 is equal to EA by 2.303 R whole T2 minus T1 by T2 into T1, right? So here T2 and T1 are the temperatures and K1, K2 are the respective rate constant. EA is the activation energy, right? So this formula is also very used. This one is also used. You can get, okay. Now what is the effect of temperature? That is what we are continuing. So what happens when we increase the temperature? You can get a theory based questions from this graph. So according to this one, what happens when you increase the temperature, the number of molecules which can react. Okay, so molecules cannot react directly, they need to possess some energy. So the number of molecules having that required energy will increase. As the number of molecules having the required energy increases, then more molecules can react, and that is when rate will increase. Okay, and then this is the graph for your Arrhenius equation. So we have just take ln on both sides, and then ln k versus 1 by t will get a negative slope. Okay, so okay, now coming to this one, effect of catalyst. This is also very important. When catalyst you use, it provides an alternative pathway and reduces the activation energy. So if you can see here in the graph, first the reaction activation energy was this much, and then the activation energy decreased. And just now I told you, if activation energy decreases, right, if activation energy will decrease, rate constant will increase, rate will increase. So that is why rate increases. So what is the role of catalyst? It provides an alternative pathway for the reaction which has a lower activation energy. Okay. Now just coming to collision theory, not like nothing much to remember. You have to just understand a few things. That first of all, the molecules are assumed to be hard spheres, and the reactions are assumed to occur only when these spheres collide with each other. Okay. Next, according to collision theory, this was the equation for rate, which is now replaced with your Arrhenius factor. Okay. Now what is activation energy? So you can also know what is collision frequency. Collision frequency is the number of collisions happening per second. Okay, so these definitions are not asked in the exam, nothing much to worry. Now this is important. Activation energy, I told you, is the minimum energy or the extra energy that is required for the reacting molecule to get converted into product. So if you see here, this was the reactant energy. See, this is the energy of the reactant, right? And after getting this energy, the reactant will start forming products. So this is called as your threshold energy. So from the reactant energy to reach to threshold energy, the energy that is required to keep or to make the reactants reach the threshold energy is called as your activation energy. Okay, so that is there. Okay. So then here you have to see, for exothermic reactions, EA forward reaction is less than the EF backward reaction. Can you just imagine this one? So if we have exothermic reactions, okay, so I can draw the graph of exothermic reactions here. So exothermic reactions means product's energy will be lesser than the reactant energy. So if you see here, what is the activation energy for the activation energy for the forward reaction is this one. The activation energy for backward reaction is this one. So which is greater? EA forward will be lesser than EA backward. Now if we have endothermic reaction, okay, so if you do endothermic reaction, the reaction is like this. Product energy will be more. Then if I find the activation energy, this is the activation energy for forward reaction, this is the activation energy for backward reaction. So EA forward is greater than EA backward. Okay, so questions can be asked from here also. Calculation based questions are asked. So just revise this topic. Okay, so these were the most important topics from chemical kinetics. Nothing much formula is there. Half-life formula, integrated rate law formulas, and then differential rate equation and rate law. Okay, so such type of easy questions, easy calculations questions are asked. So just revise this topic once and then go to our top 30 questions from chemical kinetics. Just solve them once. You will be very easily, you can complete this physical chemistry kinetics chapter. Okay, so now let us go to the next chapter, that is thermodynamics, which is very vast topic. But the good news is in the exam you do not get questions from all these topics. Very specific topics are there from which you can expect questions, and repeatedly from last 7 years the questions are asked from the same topic only. So we can, if we do that topic particularly, so we can revise it and we can do it in the exam. So don't leave this topic. Whatever I'll tell now, which you have to focus, so just focus on that thing and then go for the exam. Okay, so quick 5 to you can take hardly 15 to 20 minutes to complete this chapter if you focus only from where the questions are asked. So what are the important topics here? First one is your basic terminologies, second is work, third is internal energy, fourth is first law of thermodynamics, fifth is relation between delta H and delta U, then heat capacity, and then we have second law of thermodynamics, and then Gibbs free energy. So which is the thing that you have to most focus? Formula for work, internal energy, delta H and delta U, delta G. Okay, these 4 things you have to focus more. Okay, now let us quickly see. Here are the basic terminologies for the thermodynamics chapter. So first is, what is a system? System is the part of universe which you are considering. Open system is there can be exchange of both energy and matter. Closed system, there can be energy of only, no mass but only energy. And isolated system, there is no exchange of matter or mass, right? Neither exchange energy nor matter. Okay, now coming to surrounding. So anything except your system is called as surrounding. Boundary, the thing that separates your system and surrounding. State variables and state functions. So state variables tells about the state of a system, and state functions we have which does not depend on the initial, these are which does not depend on the path and only depend on the initial and the final state. So here you write down these examples, you have to remember. Questions are asked, which of the following is not a state function, which of the following is a state function, right? So that's why you have to remember all these examples: pressure, volume, temperature, internal energy, enthalpy, and entropy, right? Okay, let us go to the next part. Here also this, whichever I'm putting star mark, if you have not completed thermodynamics at all, these star mark things you have to do and go. Okay, so intensive properties and extensive properties. So examples here also you have to remember: temperature, pressure, density, concentration. Intensive properties are those which do not depend on the amount of substance. Extensive properties are those which depend on the amount of substance, right? So you can see volume, energy, enthalpy, entropy. Okay, now coming to here, these 3 are also important. Types of processes: isothermal, isobaric, isochoric, adiabatic. So what is constant in which pressure you should know? In isothermal, temperature constant, isobaric pressure constant, isochoric constant volume, adiabatic no heat of constant heat or no transfer of heat. Now coming to cyclic process, reversible, irreversible. So cyclic process is when initial and the final state is same, that is called cyclic process. Reversible, the process which takes in infinitely small steps, we call it reversible. And irreversible are those which occurs in a fast and cannot be come back or cannot be reversed. Okay, okay, so here it is important, all the natural processes are of irreversible nature. Okay, fine. Now we will go to our first formula, that is work done. Okay, work done, the general formula is minus P external V2 minus V1. Okay, now what happens? If the process is isothermal and reversible, then work done formula is equal to minus 2.303 nRT log of V2 by V1. First formula, second formula, very important. Okay, this formula is very important. Here we can also write this like minus 2.303 nRT, okay, log of P1 by P2. Okay, so this is the formula from where majority of the questions are asked. You have to just know the R value. Also I'll tell you what will be the R value here, 8.314. Okay, units of work done will be joule. Clear? So now if pressure, this formula either you can use or this formula you can use based on the question. If isothermal reversible is mentioned, then this formula. If nothing is mentioned, then that formula. Clear? Okay. Now let us go to the internal energy. So what is internal energy? It is the sum of all the possible types of energy present in the system. Like we have rotational, kinetic, attraction, and then vibrational. So all the sum of all the energies is called as internal energy. Then what is another definition of delta U? So it is heat change for a reaction taking place at constant temperature and volume. This is very, very important. Okay. So delta U is the heat exchange at constant volume. Next you have, so this is delta U. What is it? It is a state function and it is a extensive property. So you should know these two things, that it is a state function and it is an extensive property. Next, the value of delta U is negative for exothermic reactions and where it is positive for endothermic reactions. Clear? So if you give endothermic, means you will provide heat, internal energy will increase, so that is why delta U is positive. If you remove heat, energy will decrease, so delta U will be negative. Okay. Okay. Next, going to this one, first law of thermodynamics here also. So this is my third formula. Very, very important. Here you have to understand sign convention also carefully. So delta U is equal to Q plus W. Now here are three conditions. If the process is isothermal, okay, delta U will become 0. Then what is remaining? Q will be equal to minus W. Okay. Q is what here? Q is heat. Okay. And W is work done. I hope this one will be knowing. Okay. Now if you see, if process is adiabatic, Q is 0. Then delta U will be equal to W. Next, isochoric. In isochoric, work done will be 0. W will be 0. Then delta U will be equal to Q. Right? Once again, let us revise this one. Isothermal, delta U 0. That means Q equal to minus W. Adiabatic, Q is equal to 0. Then delta U is equal to W. Then we have isochoric. Volume is 0. Like delta V is equal to 0. So work done is 0. Delta U is equal to Q. Okay. Now, apart from this, here you should know about sign convention. So listen carefully. If work is done by the system, okay, work is done by the system, then it is negative. If work is done on the system, okay, then it is positive. Clear? This one. Now, next is about Q. If Q is supplied, okay, the system gains heat, then Q will be positive. And if system loses heat, Q is lost, okay, then it will be negative. Clear? Okay, so this is this first law of thermodynamics. Next we have enthalpy and internal energy relation. These formulas are also important. So we had formula number 4 and formula number 5. Delta H is equal to delta U P delta V, where delta H is your enthalpy. Okay, now this is your enthalpy. Okay. Now what are the properties of this one? Enthalpy is also extensive property and is also a state function. Okay. And delta H is also equal to 0 for isothermal process. Okay. Now delta H is equal to delta U plus delta NgRT. This reaction, instead of P delta V, we can write it as delta NgRT. Now how to write, how this formula has come? Like for example, you have a reaction N2 plus 3H2 gives 2NH3. Okay. Now if how to calculate delta Ng? Delta Ng will be the number of moles of products, gaseous products, minus the number of moles of the reactants. So if you see here, we have 2 moles on the product side, minus 3 plus 1, that is equal to 4. So we will get minus 2. Delta Ng value will be minus 2. Clear? Now, so that is how you can use this formula to calculate the enthalpy of any reaction. Okay. Now let us go to the next one. So heat capacity, not much questions are asked. So just you can note that basic formula. Heat capacity is the amount of heat to raise the temperature of a substance by 1 degree, dQ by dt. Specific heat capacity is to raise the temperature of 1 gram of a substance by 1 degree. So it is heat capacity by mass in grams. Okay. Next, if you see molar heat capacity is the heat required to raise the temperature of 1 mole of a substance by 1 degree, 1 mole. So that is heat capacity by molar mass. Okay. Next, this is very, very important. Okay. What is the heat capacity at constant volume is called as CV. Okay. and the formula for that is du by dt at constant volume, and Cp is dH by dt at constant volume, sorry, at constant pressure. Okay, clear? These two are very important. Then what is the relation between Cp? This is the well-known formula, Cp minus Cv is equal to R. Okay, fine. Then coming to second law of thermodynamics, here also nothing much you have to remember. You have to just know that delta S is equal to Q by T. Okay, not a very important formula. So I will write fifth, right? So we have sixth, seventh and eighth. These two formulas you might skip. That's questions are not asked from much from these questions. Then this one is your ninth formula. Okay. Next, entropy. What is entropy? Entropy is the degree of randomness. How much entropy is there? So here questions are asked, like options are given in which entropy is positive, entropy is negative. So you have to remember, if the phase is changing, okay, phase is changing, then entropy will increase. So like solid to liquid, liquid to gas. If, like for example, reactants were solid and then products are liquid, then entropy increases. Reactant is liquid, product is gas, then also entropy is increasing. Okay. Next, in that case, entropy will increase. Another case, if gaseous products are formed. Okay. Suppose the reactants are completely solid, and like in the reactant there are two gas molecules, and in the product side the number of gaseous molecules produced is more. So in that case also the entropy will increase. Another case is if number of particles increased. Number of particles increased. Like for example, in a reaction it became A2 to 2A. Here you can say there is only 1 mole, but here there is 2 moles. Number of particles has increased, so entropy will also increase. So such type of questions are also asked. Now the next very important formula is Gibbs free energy. From here many questions are asked, many questions are asked. Delta G is equal to delta H minus T delta S, this formula. Okay, and we have one more formula, that is delta G is equal to minus 2.303 nRT log K. Here, from here the conditions for what is the condition for spontaneous reaction? For that delta G should be negative. Okay, so from this condition also many questions are asked, like when delta H is positive, delta S is positive, then what should be the condition, what should be the value of T? And one more thing that you have to remember is delta G is equal to 0 at equilibrium. Okay, so these were the important concepts. Okay, now one more thing from where questions are asked repeatedly is from your Hess's law. Okay, Hess's law has no formula, but you have to practice some certain questions, like 3-4 reactions are given and you need to know one required reaction. So you have to arrange and rearrange the given equations to derive the required reaction. Then in that case, whatever enthalpies operations you are doing, that will be used for Hess's law. So in our top 30 questions from thermodynamics, many questions we have solved from Hess's law. So please do watch it. It's very easy to solve. Only you have to just know the equation and then you have to start solving it. Okay, so these are the basic important formulas from thermodynamics. Again, if I tell what you have to focus majorly is your first formula, that is work done formula. Next you have to focus on your first law of thermodynamics, that formula, and then you have to focus on delta G is equal to delta H minus T delta S. So these three formulas are the major formulas from this chapter. Okay, now let us go to the next topic, that is equilibrium. Okay, so in equilibrium we have two types of equilibrium, chemical equilibrium and ionic equilibrium. So we will first see the topics under equilibrium. First is expression for Kc and Kp, how to write. Second, we have the relation between Kp and Kc. Third, Kc and the stoichiometric coefficient. So this is also important topic. Next you have reaction quiescent and its application. Next we have Le Chatelier principle, then acid. So from here ionic equilibrium will start, acid base theory, pH of weak acid, pH of buffer, pH of salt hydrolysis, and then solubility product. Okay, so let us start with this. So first is your expression for Kc and Kp. For any reaction A, B, B gives C, C, D, D, the Kc value will be the product's concentration raised to the power of their coefficient divided by the reactant concentration raised to the power of their stoichiometric coefficient. Now, if we write that in the terms of pressure, then it will be Pc, Pd, Pa, Pv. Okay, very easy. Now, what is the relation between Kp and Kc? So, Kp is equal to Kc into Rt to the power of delta Ng. Okay. Now, same thing how we calculated delta Ng, that is number of moles of gaseous products minus number of moles of gaseous reactants. Okay. Now, here three conditions arises if delta Ng is equal to 0. then Kp will be equal to Kc, right? You can see this term, if it is 0, then RT to the power of 0 will become 1, then Kp will become equal to Kc. Now, if delta Ng is negative, right, then what I can write? Kp will be equal to, suppose it is minus 1, Kc by RT, right? So, in that case, what I can say? Kc will be greater than Kp. Okay. Now, if delta Ng is positive, then what equation will get? Kp is equal to Kc into RT. In that case, Kp will be greater than Kc. So, such three conditions arises. Okay. Now, we'll see the extent. This is also very important, Kc and the stoichiometric coefficients. So, there are three operations in Kc that you should remember. Like, for example, you have a reaction A is equilibrium with B to the power of B, and the equilibrium constant for this one is K1. Now, what you have done, you have multiplied N to the whole equation. So, what I'll get? NaA gives NBB. Now, when this N is multiplied to the whole equation, what will be the new K? The new K will be K1 to the power of N. Okay, this is the first thing that I want to tell. Now, if I want to reverse this reaction, suppose I want to write like this. BB gives AA. So, when a reaction is reversed, the equilibrium constant becomes inverse. So, now the new K for this one will be 1 by K1. Clear? Now, the third one is if two reactions are added. Like, for example, AA gives you BB, the equilibrium constant is K1, and then we have BB gives CC, and the equilibrium constant is K2. Now, if you add both these reactions, what I'll get? AA gives CC. So, when two reactions are added, the equilibrium constants are multiplied. So, K will be equal to K1 into K2. Clear? Okay. From here, questions are asked. They will give you like two equations and you have to find the K value. So, you have to remember what is done. Like the relation between the two reactions, if you can derive, then you can easily solve this question. Okay. Now, let us go to the next one, reaction quiescent. So, what is the difference between equilibrium constant and reaction quiescent? Equilibrium constant is that when you take the concentrations, the reaction has already reached the equilibrium, and the concentrations are the equilibrium concentrations of the reactants and products. But reaction quiescent is the concentration at any point time t. Okay, at any time you have taken the concentrations and you have measured the ratio, then how you can tell whether the reaction will go in forward, backward, or at equilibrium? So, we have a condition for that. If the reaction quiescent is greater than K, then the reaction will go in backward direction. If Q is less than K, then the reaction will go in forward direction. And if Q is equal to Kc, then the reaction is already at equilibrium. Okay. Now, let us see the Le-Chatelier principle. Again, a very important topic. Definition is not required to remember. Just you have to understand that if you are disturbing the equilibrium, okay, you are disturbing the equilibrium. What are the ways in which you can disturb the equilibrium? You can change the concentration, you can change the volume, you can change the temperature, and then you can change the pressure, and you can add any inert gas. Okay. So, now if you change the equilibrium, or if you want to disturb the equilibrium has like forward direction and backward direction. It will adjust itself. Okay, it will either go more in the forward or less in the backward. It will adjust itself so that the change that you have introduced will be neutralized or will be cancelled. Okay. Now, so now for that you have to remember, if you are increasing the temperature and the reaction is endothermic, okay, endothermic reaction is there and you are increasing the temperature, then the reaction will go in forward direction. If it is exothermic and you are decreasing the temperature, then it will go in forward direction. Clear? Endothermic reaction, increasing temperature, forward direction. Exothermic reaction, decreasing temperature, forward direction. And that means what? The other things will be opposite. Like if you decrease the temperature, it will go backward. If you increase the temperature, it will go backward. Clear? Second one is effect of concentration. So, concentration, if you see reactant concentration, if it is increased, then reaction will go in forward direction. Product concentration, if it is increased, reaction will go in backward direction. Then third one is effect of pressure. So, here if you increase the pressure, then the reaction will try to decrease the pressure, and we know pressure is directly proportional to number of moles. So, whichever side is less number of moles, reaction will shift to that direction. Okay. So, what is there? If increase in pressure is there, towards less number of moles. So, here there is no forward and backward. You have to just count the total number of moles, gaseous moles. So, whichever side there is less number of gaseous moles, that side it will go. Next is effect of volume. So if you increase the volume, it will go towards more number of moles, just opposite of each other. Okay. Next, effect of catalyst. There is, like, if you add catalyst, there is no effect. Now if you add inert gas at constant pressure, then it will go towards more number of moles, and at constant temperature it has towards less number. Sorry, at constant temperature it has no effect. Okay, this is actually at constant volume. Please change this one. At constant volume there is no effect, at constant pressure towards more number of moles. Clear? So all the factors are clear. Just revise it, learn it properly, and then go for the exam. Okay, now coming to your ionic equilibrium, will start. So here we have first of all 3 definitions of acids and base. Arrhenius definition is one which can donate H plus, bases give you OH minus. According to Bronsted, acid is a proton donor, base is a proton acceptor. Now here we have conjugate acid base questions are asked. Okay. So what is conjugate acid and base pair? So they differ by 1 H plus. Differ by H plus. Okay. So now if you want to find the conjugate acid, okay, conjugate acid of any X, then you have to add 1 proton. Okay. And if you want to find conjugate base of anything, okay, conjugate base of, for example, anything, then that molecule must behave as an acid, so you have to remove 1 H plus. Clear? So this thing you have to remember, and here from here questions can be asked. Then we have Lewis definition, acid is electron acceptor and base is electron donor. And then strong and weak electrolytes. Strong acids are like complete dissociation, weak acids are weak dissociation or partial dissociation. You can see examples HCl and CH3COH. Okay. Now this is very, very important slide where you have most of the important formulas. First is your pH of a weak acid. So weak acid means they will not dissociate completely, they will dissociate partially. So there is something called as a dissociation constant for a weak acid. How to calculate the dissociation constant? Ka is equal to C alpha square minus 1 minus alpha. So what is this alpha? Alpha is the degree of dissociation. How much it is dissociating? Like it will not dissociate 100%, that is clear. But whether it is 60%, 50%, 40%, 5%, right? So that is your degree of dissociation. C alpha square by, one second, this formula is, I'll change this one. Alpha is equal to root over of Ka by C. Okay, this one please change it. Alpha is equal to root over of Ka by C. Now coming to ionic product of water, concentration of H plus into OH minus is 10 to the power of 14 at normal conditions. Then pH plus POH is equal to 14. Now what is the H plus concentration if it is a weak acid? H plus concentration is C alpha, and we know we can write like this, C into alpha value I can write like this, root over of Ka into C. Now this C we can cancel and I'll get root over of Ka into C. Okay. Okay. So we will get root over of Ka into C for the H plus concentration. Okay. So once again we can discuss this one. H plus concentration for a weak acid is C into alpha. And if you see C into alpha value, I'll put this one, root over of Ka into C. So I'll get root over of Ka into C. Okay. So now if you see for the pH value, pH will be equal to half of pKa plus log C. Okay. Sorry, half of pKa minus log C. So now how this formula is coming? See, that is my A value. Like I can say now, H plus concentration is equal to root over of Ka into C. Okay. Now what we have to do? We have to calculate the pH value. pH is negative logarithm of H plus. So I can write pH is equal to minus half log of Ka into C. So this minus will be multiplied inside. So minus, I'll take half outside, minus of log Ka and minus of log C. Minus log K is nothing but pKa minus log C. So you need not derive this formula, you can just know the values, half of pKa minus log C. Clear? Now coming to buffer solutions. So buffer solutions are those which can resist the change in pH, right? Buffer are of two types, acidic buffer and basic buffer. Acidic buffer is made up of weak acid and its salt with strong base. For example, we have a weak base CH3COH, weak acid, and a strong base. So what will be the salt of this one? We will get CH3COONA, right? So these two mixture, weak acid and its salt with a strong base, will give you the acidic buffer. What is the formula? pH is equal to pKa. Whose pKa? The weak acid pKa plus log of salt concentration by acid concentration. Now similarly, we can calculate basic buffer, weak base and the salt with a strong acid. For example, you have a weak base like NH4OH, okay, and the strong acid is suppose HCl. Then we will get salt as NH4Cl, right? So this combination, weak base and a strong salt and a salt with a strong acid, will form a basic buffer. So POH will be equal to pKb plus log of salt by base. Okay. Okay, now coming to salt hydrolysis. So there are three types of salt which undergo salt hydrolysis, that is salt of a weak acid and a strong base. You can see the example. For that, what is the formula? CH3CONA is a weak acid, NaOH is a strong base, so the salt will be a salt of weak acid and strong base. So pH formula here will be 7 plus half pKa plus log C. Okay. Now strong salt of weak base and strong acid, so NH4 and Cl, right? So here the pH will be 7 minus half pKb plus log C. Now a salt of weak acid and weak base is your CH3CO and NH4. Okay. So now ammonium acetate. So 7 minus half pKb plus half pKa. Okay. So these values will be given, just you have to remember the formulas. Okay. Next is your solubility product for any salt of type AXBY. Okay. What is the solubility product? That the solubility, so x to the power of x, y to the power of y, s to the power of x plus y. For example, we have salt of barium chloride. This is x is equal to 1, y is equal to 2. So 1 to the power of 1, 2 to the power of 2, s to the power of 2 plus 1, that is 3. So we can write 4s cube. Clear? Okay. So I think, yeah. So these were the important topics from chemical equilibrium and ionic equilibrium. If you find ionic equilibrium difficult, you can leave that for now. Chemical equilibrium, Kp-Kc relation, and then how to write the expression of Kp and Kc. That things you can remember, and the stoichiometric coefficients, how it is related, this you can easily solve. Again, if you want to practice some 5-10 questions, you can watch our top 30 questions from equilibrium chapter, and then you can practice those questions for the exam. If you have any other book also, you can use it as a reference. Okay, now coming to the next chapter, very easy chapter, that is the structure of atom. Few formulas from here, if you revise, you can easily get the questions from here. So first is, let us see the topics in this chapter. We have atomic terms. We will just discuss what is atomic number, mass number, isobars, isotopes and all. Then we have electromagnetic waves, atomic spectra of hydrogen. This is important. Then photoelectric effect, Bohr's model, de Broglie hypothesis and Heisenberg uncertainty principle, quantum numbers and rules for filling of electrons. Okay. Yeah. So we will discuss again, if I tell which are the most important, this one, electromagnetic waves, Bohr's model, de Broglie hypothesis and Heisenberg quantum numbers. Yeah, you can say like 1, 2, 3, 4, 5 topics out of 8 are very important. Like questions are picked from these topics. Okay. Now quickly let us revise the atomic terms. Atomic number Z is the number of protons. Mass number is the number of protons plus number of neutrons. Okay. Then nucleons is present inside the nucleus, that is protons and neutrons. Isotopes are same atomic number, different mass number. Isobars, the opposite, same mass number, different atomic numbers. Isotones are that those who have same number of neutrons but different number of protons or mass numbers. Then you have isoelectronic species. These are the species having the same number of electrons. So quickly you can revise it, very easy definitions. Next, coming to wave, this is important. What is these definitions are not important, but the formulas are important. Wavelength is what? Distance between two neighboring crust or two neighboring trough. So if you have seen, we have a wave like this, right? I draw. So between two neighboring, the distance between two neighboring crust or two neighboring trough. So this is called as your wavelength. Then frequency is the number of cycles that has been completed in 1 second. Here this formula you have to remember, C is equal to lambda into mu. wavelength, frequency, speed of light. Okay. Now wave number is number of wavelengths per centimeter, velocity is the distance traveled by the wave per second, amplitude is the height of the crest or the top. Okay. Now coming to this one, hydrogen spectra. This is very important. In hydrogen spectra, like what does it tell? When electron goes from one level to another level, it emits radiation, right? For example, we have different energy levels for hydrogen. When an electron jumps from one level to another level and then when it comes back, it emits the radiation. We have to calculate the wavelength or the energy of this emitted radiation. Okay, so the formula for that is equal to 1. So in this formula, we are calculating the wave number. Okay, wave number of the emitted radiation. Clear? When electron jumps from one level to higher level and then when it comes back to the lower level, it emits radiation. We want to calculate the wave number of this emitted radiation. The formula for that is RH into 1 by N1 square minus 1 by N2 square. So N1 you have to remember is the lower value and N2 is the higher value. It means suppose an electron jumps from 5 to 2, right? So N1 will be your 2, N2 will be your 5. Clear? Now in this RH value is 109,677 centimeter inverse. Okay. Now based on the destination, like from wherever it starts but where it reaches, based on that we have a different spectra of hydrogen. So if the N1, see here, if the reaching point means from wherever it excited level, it ends at N1 is equal to 1. Okay, it ends at the first orbit, then we call it as Lyman series. And this energy or this emitted radiations from any level to N1 level lies in the UV region. Now if it ends at like second N2, whatever radiation stops at second energy level, we call it Balmer series, and this one comes in the visible region. If all the radiation end at third region, third energy level, then we call it as Paschen series, and this falls in the IR region. Similarly, if the energy of the electrons stop at fourth energy level, we call it bracket, and this also forms in the IR region. And if the electron stopped at the fifth orbit or fifth energy level, we call it P fund, and it is also IR radiations. Clear? Okay, next we will go to photoelectric effect. Very simple thing. Let us quickly revise. So when the ejections of electrons takes place from the surface of the metal when light of suitable frequency falls on it. So any metal is there, you put light of suitable frequency, electrons will be ejected out. Then the minimum frequency required for the ejection of electrons is called as threshold energy. So any energy will not do, any minimum frequency is required. That minimum frequency is called as your threshold frequency. The energy of ejected electrons is directly proportional to the frequency of the radiation. Next, number of electrons ejected per second depends on the intensity of the radiation. Now what is this one? H nu is equal to H nu 0 plus half mv square. So this is the energy of radiation, okay, which you are putting on the metal. Now this is the minimum energy required, or we can say threshold energy. Okay, so now suppose, now this one is the kinetic energy of the electron. Okay, so just you can understand, to remove an electron you need suppose 5 joules of energy. You have given 12 joules of energy. So 5 joule out of that 12 joules of energy that was given by the radiation, 5 joule was used for just putting to remove the electron from the nucleus. Then the rest 7 joules will be used as the kinetic energy of the electron. Okay, so that is the formula. H nu is equal to H nu 0 plus half mv square. Here nu 0 is called as your threshold frequency, H nu 0 is called as the threshold energy. Okay. Okay. Next we'll go Bohr's model. So Bohr's model is very simple. Electrons revolve around the fixed orbits. You don't have to remember these all things, but you have to know. And then the angular momentum is an integral multiple of h by 2 pi. Then when electrons absorb energy, they go to the higher level, and when they release energy, they come to the lower level. Then energy absorbed or released depends on the delta E, that is E2 minus E1 equal to h nu. Now here some important formulas you have to know. The energy of any orbit is minus RH by 1 by n square. For a hydrogen-like species, what do you mean by hydrogen-like species? The number of electrons will be same. And the radius of nth orbit is given by 52.9 dot n square by z picometer. Energy of nth orbit minus 2.18 into 10 to the power of minus 18 z square by n square unit is joule. Minus 13.6 z square by n square unit is EV. 313.6 z square by n square calorie per mole. These two units you have to remember. Now velocity of any orbit 2.18 into 10 to the power of 8 z by n. So where n is equal to 1, 2 and 3. Okay. So you have to remember which formulas from here. This one and this one and this one. Okay. Very simple one. Next, let us quickly finish de Broglie hypothesis. According to this, what happens? Even the matter can behave as a wave. So if they are behaving as a wave, they will have a wavelength. So the formula to calculate the wavelength of the matter wave is your lambda is equal to h by mb or h by p, where m is the mass, v is the velocity, h is the Planck constant, 6.63 into 10 to the power of minus 34 joule seconds. Okay, and p is the momentum. Right, so I'll write here mass and velocity. Now, what is Heisenberg uncertainty principle? According to this principle, the position and momentum cannot be determined simultaneously. Delta x is the uncertainty in position, delta p is the uncertainty in momentum. This is greater than or equal to h by 4 pi m, where h is the Planck's constant, okay, and 4 pi m is the mass. Okay, so we cannot calculate the position and momentum exactly accurately simultaneously. Okay, if you calculate position correctly, momentum there will be some error. If you calculate momentum correctly, position will have some error. Okay. Now we will discuss the next thing, that is quantum numbers. Very easy thing and important also. Principal quantum number, the value starts from n to 1, 2, 2, 3. What information it gives you? It tells you about the energy of the shell. Next is your azimuthal quantum number. Its value starts from L is equal to 0 to L is equal to n minus 1. And what does it tells you? It tells you about the subshells. Or we can say it tells you about the shape of the orbitals. Next one is your magnetic quantum number. Its value lies from minus L to plus L. What does this information tells us? This information tells about the orbitals, or we can say their orientation. Spatial orientation, how, in which direction, x direction, y direction, z direction, which direction the orbital lies. Then spin quantum number tells about the spin of the electron. Its value is plus and minus half. Let us take an example for this one. Suppose n is equal to 3. Okay, so n is equal to 3. Then what are the possible L values? That is your azimuthal quantum number. If you see, what are the range of L value? 0 to n minus 1. N is 3 here, n minus 1 means 3 minus 1, 2. So the possible L values are 0, 1 and 2. Okay. Then what are the possible ML values? So if you know, for 0 S is used, for 1 P is used, and for 2 D is. Okay. Sorry. 1 second. Yes. SPD. Okay. So now if you see, we have 3. So what is this subshell name? 3S. This is 3P and this is 3D. Now if you want to calculate ML values is from minus L to plus L. So minus 0 to plus 0, there will be like it is 0 only. So here only 1 ML value will be there. So 3S will have only 1 orbit. Now if you see ML for 1, so this is minus 1, 0 and plus 1. Right. So minus 1, 0, plus 1 as having 3 values. So we tell it as 3P has 3 orbitals. Next, if you see 3D, minus 2, minus 1, 0, plus 1 and plus 2. So there are 5 orbitals here. Right. So here if you see, these are 3D orbitals. Then in this 3D subshell, there are 5 orbitals. Right. So that is how you can do. Next is node. What is node? Node is the position or the place where the probability of finding of electrons is 0. So there are 2 types of node, radial nodes and angular nodes. Radial nodes formula is n minus L minus 1. Angular nodes is formula is L. Total number of formula is n minus 1. For example, given 3D. Okay. In 3D orbital, how many nodes are there? So if you come to calculate, what is the n value? 3. What is d value? 2. Now the total nodes if I want to calculate, that will be 3 minus 1, 2. Now if I want to calculate radial nodes, that is n, that is 3 minus L minus 1. So again this is 0. Then if I want to calculate angular nodes, that is L, which is equal to 2. Right. So we can calculate in this way. Okay. Okay. Now we can just see some rules that has been the statements you can know while filling the electrons that you have to keep in mind. So first is our Aufbau principle. What it tells us that electrons should be filled in the increasing order of the energy levels. So electrons are added one by one to the various orbitals in order of their increasing energy. The one which is having least energy will be filled first, then the one which is having more energy will be filled at last. Correct? Okay, next. In neutral isolated atom, the lower the value of n plus L, the lower is the energy. So how you will know which orbital is having how much energy? We have to follow n plus L rule. Now for example, if you have 3s and 2p, what is the n value here? 3, L value is 0. Okay, then here n plus L, 2 plus p value is 2. Sorry, p value is 1. 1 second. Yeah, p value is 1, so that is also 3. So if when both n plus L value comes together or comes the same, then we have to consider whose n value is less, its energy is less. Like for example, here n value is less 2, so 2s value will be 2p value will be less than 3s. So in that way we can calculate and we can tell the order. So first 1s, then 2s, then 2p, 3s, 3p, 4s and 3d. This one you can check. 4s value is 4 plus 0, 4, 3d, 3 plus 2, that is 5, right? So this value is coming higher, so that is why its energy is higher, and first 4s will be filled, then 3d will be filled. Similarly, 4p, 5s, 4d, 5p, 6s, 4f, 5d. This rule you should know. Now next is Pauli's exclusion principle. What does this tell? An orbital contain a maximum number of 2 electrons and these 2 electrons must have the opposite spin. So whenever you fill the electrons in an orbital, you must represent in this way. They are in the opposite spin. Okay. Next, Hund's rule of maximum multiplicity. So this tells us electron pairing in p, d and f orbitals cannot occur until each orbital of a given subshell contains 1 electron each or is singly occupied. Now for example, you want to fill p5. Okay, so what you have to do is, in p there are 3 orbitals, 1, 2, 3, 4, 5. You cannot fill in this way. This is the wrong way of filling. What you have to do is, you have to first fill one. Okay, let me take the example of p3 first. Okay, if p3 is there, you cannot fill it like this. This is incorrect because one orbital is still empty. So first you have to give 1 electron to all the orbitals and then pairing of electrons will start. So what should be the correct way of filling it? We can fill it in this way. We can fill it in p1, then here 3 electrons first you have to give to each orbital. Now p4 is there, then it will start pairing. Clear? Okay, so yeah, so these were the important concepts, important topics to revise from your structure of atom. So once again, if I revise, I'll recollect, like you have to revise the Bohr's formula. Okay, then you have to revise the Heisenberg uncertainty principle. Then you have to revise de Broglie hypothesis. Photoelectric effect questions are less, so just you can draw the formula. Then you should know this formula that hydrogen atomic spectra questions are a must. So prepare atomic hydrogen spectra properly. Clear? Okay. So now we will go to the last topic, and like very easy topic, some basic concepts of chemistry. This topic is like the backbone of the whole physical chemistry. You should know important formulas from this chapter definitely. So now let us see. First one, what are the chapters in or the topics in this chapter? Laws of chemical combination. Second is mole concept. Third is percentage composition, molecular formula and empirical formula, limiting reagent, and then you have concentration terms. Okay. Now let us see these topics in detail. First is your laws of chemical combination. So we have 5 laws. First is your law of conservation of mass. According to this, mass can neither be created nor be formed. Law of constant proportion, it tells that a chemical compound always contains same elements in definite proportion by mass. It does not depend on the source of the compound. Like for example, if you have taken water molecule, what is the mass ratio? You have hydrogen is 2 and oxygen is 16. So 1 is to 8, right? So whenever you take water from any source, the mass ratio of hydrogen and oxygen will always remain constant. Next, law of multiple proportion. When 2 elements combine to form 2 or more than 2 different compounds, then the different masses of one element B, which combine with the fixed mass of other element, bear a simple ratio to another. So like for example, we'll take the example CO and CO2, right? What is the mass of carbon? 12, oxygen mass is 16. Here carbon mass is 12, oxygen mass is 32. So here, which mass is fixed? Carbon mass is fixed. So if you take the ratio of oxygen from both, it will get a simple number ratio. So what is the mass of oxygen in CO16? What is the mass of oxygen in CO2? 32. So 1 by 2 will get 0.5. It is a simple whole number ratio, right? Okay, simple ratio, sorry, not simple whole number ratio, simple ratio. Next, coming to law of reciprocal proportion. So if two elements B and C react with the same mass of a third element A, the ratio in which they do so will be the same or simple multiple if B and C reacts with each other. Okay. Next one, coming to Gay-Lussac's law of volume. It is very similar to law of conservation of mass, but it is in terms of volume. So if you have at a given temperature and pressure, the volume of all gases and reactants products bear a simple whole number ratio to each other. So the ratio of the reactants and the ratio of the reactants to volumes is also a simple ratio. Okay. So let us see the next topic, that is your mole concept. So what is there in mole concept? 1 mole of anything, you know, it occupies just 6.022 into 10 to the power of 23 particles. And what is mole? It is a unit of amount of substance, right? Unit of amount of substance. Now, what is there, like how to convert from one? So there are four ways of representing the amount of substance. So what are the 4 ways? One is your mass, okay. Another is your number of particles, mass, number of particles. Then another is volume, okay. And the fourth one is number of moles, okay. Now these are the 4 ways by which we can represent the amount of substance, okay. Now see, if we know number of moles and you want to calculate mass, so what you have to do? You have to multiply with molecular mass, okay. Now similarly, if you know the mass and you want to calculate the number of moles, then you have to divide by molecular mass, okay. Mm stands for molecular mass. Now number of particles and number of moles. So if we know number of moles and you want to calculate number of particles, then you need to multiply with Avogadro number. And if you have number of particles and you want to find number of moles, you have to divide by Avogadro number. This is called as your Avogadro number. Now from number of moles to volume. So if you have number of moles and you want to calculate volume, you have to multiply with 22.4. And if volume is there and you want to calculate number of moles, you have to divide by 22.4 liter. So this one has to be there under STP condition, standard temperature and pressure condition. What is standard temperature, pressure? Temperature should be like 0 degree, pressure should be 1 atm. Okay. Now let us see the next one, percentage composition, how to find out. So the mass of the element in the compound divided by the molecular mass of the compound into 100. Like for example, a quick one, suppose we take H2O. Okay, what is the percentage of hydrogen in H2O? So the mass of hydrogen is 2, molar mass of water is 18, 2 by 18 into 100. Like this you have to calculate. Next is molecular formula and empirical formula. What is molecular formula? So molecular formula represents the actual number of each individual atom in any molecule. Empirical formula represents the smallest whole number ratio in the constituent atom within the molecule. For example, you take glucose. Okay, glucose actual formula is this one. And empirical formula means you have to take the ratio of all the atoms. So we can cancel 6 ones are 2s are 1s are CH2O. This is the empirical formula and this is the molecular formula. Okay. Now, molecular formula will be equal to empirical formula into N. Okay. Now, molecular weight is equal to N into empirical weight. So just you have to multiply this one. Molecular weight, one more formula is there, is also equal to 2 into vapor density. Okay. Okay, now how to calculate empirical formula also we'll see one small example. Suppose you have A, B and C. Okay, their percentages are given. Suppose this is 20, 30 and 40. So what you have to do, and their molecular masses are Ma, Mb and Mc. Okay, now first of all you have to calculate the number of moles. So number of moles will be given mass by molar mass. So here I will get 20 by Ma, right? Here I will get 30 by Mb and here I will get 40 by Mc. Now after you get the number of moles, you have to find the simple ratio. Okay, so here what you have to do, you have to divide out of these number of moles, whichever is the smallest one, divide the whole by that number, right? Then you will get a simple whole number ratio. Now if this is coming in, like whole numbers are coming, it is fine. If not, then multiply a constant to all the 3 values to get the final whole number value. Clear? So empirical formula is very easy. Questions are asked from here. Next, if you see limiting reagent, so the reactant which is totally consumed during the course of the reaction, and when it is consumed the reaction stops, that reagent is called as your limiting reagent. How to find a limiting reagent? First you have to balance the reaction. Next, suppose number of moles of A and mass of A is given or mass of B is given. Find the number of moles of A and find the number of moles of B. Okay. Now, if number of moles of A by B, okay, this ratio, number of moles of A by B is greater than number of moles of B by A. Okay, in that case, which one will be your limiting reagent? B will be the limiting reagent. Similarly, if this one is greater, right? In that case, A will be the limiting reagent. Clear? Very easy to find out. Next, concentration terms. So we'll see the concentration terms, important one, mass percentage. So mass of the solute by mass of the solution into 100. Mass of the solute by mass of the solution into 100. Next, mass by volume percentage. So mass of the solute, okay, mass of the solute by volume of the solution into 100. Okay. Next, volume by volume percentage. So volume of the solute by volume of the solution into 100. Clear? Next, we have parts per million. So mass of the solute by mass of the solution into 10 to the power of 6. Then mole fraction, we have also already discussed. Number of moles of A by number of moles of A plus number of moles of B is called as mole fraction. Now molarity we have discussed in the solutions chapter. Number of moles of solute by volume of the solution in liter. So that is, we can write it again here. Number of moles of solute means what? Given mass by molar mass into 1000 if the volume is in ml. Now molality will be W by M into 1000 by W, right? So here it is weight of the solute in gram. So here I will write WB, this is B and this is A. Okay. Okay. So finally we have discussed all the important topics, important formulas, and I have also told you which things you must focus in the particular chapter. So only one day is left. So now you can just, if you haven't done any chapter, you can just give a revision to these important topics. And if you have already studied, so focus on these topics once again, review these concepts again, do some numericals from this. Okay. So these are the complete physical chemistry revision. If you have found this video helpful, please like, share and subscribe our channel. All the very best for your COMEDK examination.